This is a lesson on temperature in the heat and thermodynamics unit. What is temperature? That's a really good question. Physicists think of it as a measure of internal energy. Regardless of phase, there's molecules translating, rotating, and vibrating within a substance. And so we're going to relate that energy of all those movements to the temperature. That's what temperature is on a conceptual level. So the more energy results in faster translation, vibration, or rotation. And you can think about that with these gas molecules here. If they're moving around faster, they're going to have a larger kinetic energy. By measuring temperature, we were measuring physical properties of the substance affected by this kinetic energy at a molecular level. And so an implication of this that you will keep as you move forward is if we are at absolute zero temperature, that means there's absolutely no motion. Since temperature relates to the physical properties of a substance, that's how we would measure temperature. Any physical property that responds to changes in temperature predictably, reproducibly, and reliably are viable ways for us to measure temperature scientifically. So just like you would see with a regular mercury thermometer, we would measure a change in the dimension of the liquid. It gets taller or shorter depending on the temperature. Since dimensions change, we can measure the dimension of an entire solid, where we might have a physical thermostat. Electrical resistance changes in response to temperature changes. Color changes in response to temperature changes, and we can see that with heat-sensitive liquid crystal, which you may see in a regular doctor's office if they take your temperature with a temperature strip. Finally, an amount of emitted light in the form of radiation can also alert us to the temperature value. We have 3 scales with which to measure temperature: Fahrenheit, Celsius, and Kelvin. And you will see Celsius and Kelvin being used more frequently in science. The temperature scales on Earth are based off a substance, and we could have used any substance, but water is a common substance across the cosmos that's reliable in ways that we can measure. So here's a little bit of a history lesson understanding how temperature scales work. Fahrenheit took a piece of glass and he marked markings on it, and then he stuck it in freezing water and then boiling water. And he noticed the value of the marks on his scale at freezing and at boiling. So that's freezing and boiling. And we can see that on the Fahrenheit scale over here. Celsius was a little bit more clever about it. He marked 0 as freezing and 100 as boiling, and then divided that distance on his scale evenly from 0 to 100. So that's how that scale was made up. Kelvin is an additional scale that goes all the way down to absolute 0. Absolute 0 is 0 on the Kelvin scale, not on the Celsius scale. 0 Kelvin happens to be 273 and some change degrees Celsius. So those scales are the same value between each degree, and then there's a different scale for the Fahrenheit. You are expected to be able to convert between temperature scales. These scales are linear. A heated substance expands with linear dependence on its length, and we'll see this in the lecture about thermal expansion. Temperatures on one scale can be converted to temperatures on the other. So here's the one from Fahrenheit to Celsius. Here's also the one from Celsius to Kelvin. So if you're given in Fahrenheit, there's no direct equation you'll be given. You'll need to convert to Celsius and then to Kelvin. The problem I picked out for us is a beautiful example of linear modeling. You create a thermometer of a container and some fluid you have laying around. I don't know what this fluid is. To make the thermometer, you mark the level when you put it in boiling water. Then you mark the thermometer when you put it in freezing water. So now you have a mark for boiling and freezing, just like Celsius and Fahrenheit did. You then divide the distance between those marks into 2 to the 7th, which is 128 even divisions. You divide it in half, and then in half, and then in half, and then in half. It's kind of clever that you did that. So determine an equation for converting your temperature scale to Fahrenheit, Celsius, and Kelvin. So let's think about this. We're going to do linear modeling. So overall, we're going to want an equation that follows y equals mx plus b. And if you know how to write a line, we need to figure out the slope, and therefore we need to figure out the input variables and the output variables. Well, the input variable for this problem, because you have your temperature and want to convert it to the other temperature scales, the x variable will be your temperature. So your temperature. The output variable will be one of the other scales. Other scale. Okay? So let's get some x and y values going. That seems like the right thing to do. You made a couple of measurements, first at freezing and then at boiling.
So let's write out what we know. For your temperature, freezing was 0 and boiling was 128 even divisions. We know for Fahrenheit, it freezes at 32 and it boils at 212. For Celsius, we know it freezes at 0 and it boils at 100. And I'm not going to write down Kelvin because if we know how to find Celsius, we know how to find Kelvin easy. For part A, let's pick out 2 points in which to find our slope. Our input variable is the x value, which is your temperature, and the output is the Fahrenheit temperature. So here's the input. We have a point 032. So that's your temperature and the other scale. And then we also have point 128, 212. So we can find a slope for this. The slope equals 212 minus 32 over 128 minus 0. This gives you 180 over 128, which simplifies to 45 over 32. It's not as nice as the 9/5 in the Fahrenheit Celsius equation, but it works. So that's the slope for our equation. So if we want to find the temperature in Fahrenheit, we would take 45 over 32 and multiply it by your temperature in your scale. And then we know the intercept value. Okay, if we plug in 0 here, what do we expect the temperature in Fahrenheit to be? Well, when we plug in 0, we expect to get 32 out. And so that's our y-intercept. And that's the equation for part A. It's a linear equation. We just pick 2 points and we can find our equation. Let's do the second part, B, Celsius. So again, we need to pick our 2 points. Our 2 points are now going to be your temperature and the Celsius scale. So this is x and this is y. So our first point will be 0, 0, and our second point will again be 128 and then 100 in this case. So let's find our slope. The slope equals 100 minus 0 over 128 minus 0, which is 100 over 128. When you simplify that, you can divide by 4 on both top and bottom, and you get 25 over 32. Same denominator as the top. So let's plug this into our equation. If you want the temperature in Celsius, we will take 25 over 32 times your temperature, and then we will add on the initial value. When we plug in 0 for your temperature, we should get 0 out for the Celsius. So this is actually 0 on the end, and you could omit it if you like. So that's our answer for part B. Part C asks, what's the Kelvin? Well, I know Kelvin is 273.15 plus the Celsius. So if I want the temperature in Kelvin, I would take the temperature in Celsius and add 273.15. So then I'm just going to take this and plug it in here where I know that. So the temperature in Kelvin is going to equal 25 over 32, your temperature, plus the 273 to switch scales. And those are the answers for this problem.